Boron nitride is a heat and chemically resistant refractory compound of boron and nitrogen with a chemical formula Bn. It exists in various crystalline forms that are isoelectronic to a similarly structured carbon lattice. The hexagonal form corresponding to graphite is the most stable and soft among Bn polymorphs, and is therefore used as a lubricant and an additive to cosmetic products. The cubic, sphalerite structure, variety analogous to diamond, is called CBN. It is softer than diamond, but its thermal and chemical stability is superior. The rare wurtzite Bn modification is similar to lonsdaleite and may even be harder than the cubic form. Because of excellent thermal and chemical stability, boron nitride ceramics are traditionally used as parts of high-temperature equipment. Boron nitride has potential use in nanotechnology. Nanotubes of Bn can be produced that have a structure similar to that of carbon nanotubes, i.e. graphene, or Bn, sheets rolled on themselves, but the properties are very different. The most stable crystalline form is the hexagonal one, also called HBN, alpha Bn, GBN, and graphitic boron nitride. Hexagonal boron nitride, point group equals D6H, space group equals P63/mmc, has a layered structure similar to graphite. Within each layer, boron and nitrogen atoms are bound by strong covalent bonds, whereas the layers are held together by weak van der Waals forces. The interlayer registry of these sheets differs, however, from the pattern seen for graphite, because the atoms are eclipsed, with boron atoms lying over and above nitrogen atoms. This registry reflects the polarity of the Bn bonds. Still, HBN and graphite are very close neighbors, and even the BC6N hybrids have been synthesized where carbon substitutes for some Bn atoms. Hexagonal Bn, HBN, is the most widely used polymorph. It is a good lubricant at both low and high temperatures, up to 900 degrees Celsius, even in an oxidizing atmosphere. HBN lubricant is particularly useful when the electrical conductivity or chemical reactivity of graphite, alternative lubricant, would be problematic. Another advantage of HBN over graphite is that its lubricity does not require water or gas molecules trapped between the layers. Therefore, HBN lubricants can be used even in vacuum, for example in space applications. The lubricating properties of fine-grained HBN are used in cosmetics, paints, dental cements, and pencil leads. Hexagonal Bn was first used in cosmetics around 1940 in Japan. However, because of its high price, HBN was soon abandoned for this application. Its use was revitalized in the late 1990s with the optimization HBN production processes, and currently HBN is used by nearly all leading producers of cosmetic products for foundations, makeup, eyeshadows, blushes, kohl pencils, lipsticks and other skincare products. Because of its excellent thermal and chemical stability, boron nitride ceramics are traditionally used as parts of high-temperature equipment. HBN can be included in ceramics, alloys, resins, plastics, rubbers, and other materials, giving them self-lubricating properties. Such materials are suitable for construction of, for example, bearings and in steel making. Plastics filled with Bn have less thermal expansion as well as higher thermal conductivity and electrical resistivity. Due to its excellent dielectric and thermal properties, Bn is used in electronics, for example as a substrate for semiconductors, microwave transparent windows and as a structural material for seals. It can also be used as dielectric in resistive random access memories. Hexagonal Bn is used in xerographic process and laser printers as a charge leakage barrier layer of the photo drum. In the automotive industry, HBN mixed with a binder, boron oxide, is used for sealing oxygen sensors, which provide feedback for adjusting fuel flow. The binder utilizes the unique temperature stability and insulating properties of HBN. Boron nitride nanosheets, HBN, can be deposited by catalytic decomposition of borazine at a temperature ~1100 degrees Celsius in a chemical vapor deposition setup, over areas up to about 10 square centimeters. Owing to their hexagonal atomic structure, small lattice mismatch with graphene, 2%, and high uniformity, they are used as substrates for graphene-based devices. Bn nanosheets are also excellent proton conductors. Their high proton transport rate, combined with the high electrical resistance, may lead to applications in fuel cells and water electrolysis.